Welcome to Visual Algebra Lecture 2.5, Groups of Permutations. In this lecture, we will see several notations for encoding permutations of finite sets, with a so-called cycle notation being our preferred. After a bit of practice with that, we will learn how to encode permutations with matrices. These rearrange entries of column vectors and row vectors, but in different ways. Cayley's theorem says that every finite group is isomorphic to a collection of permutations, and we will see two ways to find such permutations, one using a Cayley graph and the other using a Cayley table. Okay, let's go. Loosely speaking, a permutation is an action or operation that rearranges a set of objects. Formally, if X is a set, then a permutation of X is just a bijection from that set to itself. The permutations of a set X form a group that we denote by Sx or perm of S. Now, X does not have to be finite, but in most cases in this book, we will be looking at finite sets, and a common special case is when X is just the numbers from 1 up to n. We call this the symmetric group and write it S sub n. Though honestly, if X is an arbitrary set, we often call this the symmetric group as well. But in this class, when you hear symmetric group, you can think of it as the set of permutations of a finite set of numbers 1 up to n. If X and Y have the same cardinality, then the symmetric groups over X and Y are isomorphic. So this is why if we're dealing with finite sets, we'll usually just work with Sn. And this has order n factorial, which is n times n minus 1 all the way up to 2 times 1. That's just the number of permutations. It's a basic discrete math fact. There are several notations for permutations, each with their strengths and weaknesses. And it's best to just show you this with an example. So throughout, we'll take a permutation pi on 6 elements, so the numbers 1 up to 6. And the most basic way to write this is with a table. So for each of the inputs, 1 up to 6, we write the corresponding output. So this just says 1 gets mapped to 2, 2 gets mapped to 3, 3 gets mapped to 1, and so forth. So if you do this for all permutations, then you don't really need this top row because it's just always 1 up to 6. So often what happens is people just take this bottom row and they say that is the one-line notation of this permutation. Next, we can represent this, or visualize it nicely with a diagram. Permutation diagram, where we just draw the numbers 1 up to 6, and we draw arrows. So 1 gets mapped to 2, we draw an arrow from 1 to 2, 2 gets mapped to 3, 3 gets mapped to 1, again, refer back to here. 4 gets mapped to 6, 6 gets mapped to 4, and notice that 5 doesn't have an arrow because it gets mapped to itself. Now, it's not wrong to draw an arrow, some people do it, but it's just not necessary, so we usually omit it. Finally, the cycle notation. This is going to be our preferred notation because it's more concise. And so 1, 2, 3 here means that so this corresponds to this cycle. 1 goes to 2 goes to 3. And then 4 and 6 means 4 goes to 6, 6 goes back to 4. And then 5 is omitted because it's a fixed point. If we want to, we can write it like this, but that's not necessary because any missing numbers, as long as we know what the maximum number n is assumed to be a fixed point. Okay, let's go through these notations again and talk about some pros and cons. So the one-line notation for the permutation on the previous slide was 2, 3, 1, 6, 5, 4. And pros of this is concise. It's a nice visualization of a rearrangement. You can see what gets shuffled around where. Some cons of this is it's bad for combining permutations. So here are 2 permutations, and let's say, what happens when I first do this permutation and then that one? It's not clear at all in this notation how to do that. And we'll see that our other notations, it's easier. It's also not clear where elements get mapped. So like, where does 4 get mapped to? You have to like count 4 spaces and say, oh, 4 gets mapped to 6. Right away, it's not as obvious as like with one of those permutation diagrams with the arrows. And it's also hard to compute the inverse. This is similar to bad for combining permutations. If I wrote the inverse right next to this, you probably wouldn't recognize it as the inverse. For a permutation diagram, here are those same permutations. So this one here, sigma 5 goes to, or 1 goes to 5, 2 goes to 6. So 1 goes to 5, 2 goes to 6, 3 goes to 4, etc. So pros are you can see where the elements get mapped. It's pretty clear. Where does 4 get mapped to up here? You just look at it. It's easy to compute inverses. Just reverse the arrows. That's the inverse. And it's convenient for combining permutations. And I'll show you how to do this in a couple of slides if you don't see it already. So if you want to do this permutation and then that one, 1 goes to 2, and then 2 over here goes to 6. So the net effect is 1 goes to 6. Some cons of this notation are that it's cumbersome to write. So there's all these arrows, and it can't get tangled, especially if you have permutations on like 8 elements and there's a lot of zigzagging in here. It's hard to figure out what this thing looks like. Finally, the cycle notation, which will be our preferred. Some pros for this are that it's short and concise. It's a lot less writing than at least this one. Maybe it's arguably not less than this one, but it's easy to see the disjoint cycles. You can see, just like you can here, that you have a cycle of 1, 2, and 3 here, and 4 and 6. You can't really see that up here as obvious, especially if they're more intertwined. And here's the cycle notation of this one. So to see how I got this, if I start at 1 and I just trace it out, 1 goes to 5, which goes to 2, which goes to 6, which goes to 3, which goes to 4, which goes back to 1. 1 goes to 5, goes to 2, goes to 6, goes to 3, goes to 4, and back to 1. Another pro is that this notation is convenient for combining permutations, and I'll go over that shortly. But some cons are that the representation is not unique. And well, up to a point it is. So I can write this cycle here. I said 1 goes to 2, goes to 3, goes to 1, like this. So let's go up here. This cycle is 1 goes to 2, goes to 3, goes back to 1, but it's also 2 goes to 3, goes to 1. So I could start really anywhere here. So up to like cyclic ordering, and also it doesn't matter if I write 4, 6 first or 1, 2, 3 first. You don't have uniqueness. And finally, it's not necessarily clear what n is. If I write this down, you know n is equal 6. If you write this down, you know n equals 6. If you write this down, you don't know. Maybe you are in S7 and just 7 is a fixed point. But these cons, as we'll see, are minor. This will be our preferred notation. I said this in passing on the previous slide, but let me write it down now. The cycle 1, 4, 6, 5 means 1 goes to 4, which goes to 6, which goes to 5, which goes back to 1. So there's 4 ways to write it because we can start with any of these digits. So if we start with 4, we say 4 goes to 6, which goes to 5, which goes to 1, which goes back to 4. I write it like this. To find the inverse of a cycle, one way to do it is just write it backwards. So the inverse of 1, 4, 6, 5 is 5, 6, 4, 1. A lot of people like to start with the smallest digit. So if you start with the 1, this becomes 1 goes to 5, or 1, 5, 6, 4. Let me point out something that you've probably already noticed, which is every permutation in Sn can be written in cycle notation as a product of disjoint cycles. And this is unique up to commuting cycles and cyclically shifting cycles. And by cyclically shifting, I mean each cycle we can write multiple ways like this. And by commuting, well, I mean disjoint cycles commute. And that's best seen with an example. Here's a permutation in S10 written as a permutation diagram or in cycle notation. And I hope that it's clear that if I shuffle these 4 elements, 1 goes to 4, goes to 6, goes to 5, goes back to 1, and I shuffle 8 goes to 10, goes to 9, goes to 8. By shuffle, I mean permute. The order that we do those doesn't matter. These things do not interfere with each other. So this permutation, which is a product of how many cycles? Be careful. 4 cycles, because 7 is a fixed point. We don't usually write it, but that is still a cycle. But since these are disjoint, they commute. So I can write them in any of these orders that you see here. 1, 4, 6, 5, 2, 3, 8, 10, 9, or 2, 3, 8, 10, 9, 1, 4, 6, 5, and so on. Another remark, the order of a permutation is the least common multiple of the sizes of its disjoint cycles. Maybe I have an example here, but let me start with a simpler one. If I have the cycle 1, 2, 3, and then 4, 5, maybe it's easier if I draw it out like this, you can see that there's a 3 cycle here and a 2 cycle here. And how many times do you have to apply this permutation to get back to where you started? Well, every third step. So think of these as people sitting in chairs, and they're cyclically shifting these 3 seats and these 2 seats. So every third time step, these 3 will be back in the original order, and every second time step, these 2 will be back. So every 6th time step, they will both be back in the original order. For a more complicated example, in S10, this permutation, 1, 3, 8, 6, 2, 9, 7, 4, 10, 5, has order 12, because this is a 4 cycle and this is a 6 cycle, and the least common multiple is 12. That's how many times you have to apply this cycle to itself for this 4 cycle to become the identity, and this 6 cycle or powers of it to become the identity as well. When cycles are not disjoint, the order matters. So 1, 2, 1, 3 is not equal to 1, 3, 1, 2. Now, this is an important thing to note. Many books compose permutations from right to left due to function composition. And there's good reasons to do this. In this book and video series, I have been using right Cayley graphs, where multiplication is left to right. And it would only make things more confusing if I switch that up and do permutations right to left. So we will compose permutations in this book from left to right. That means, given pi and sigma as permutations in Sn, anytime that I write pi sigma, what I mean is first do pi and then do sigma. The main drawback about our convention is that it does not work well with function notation applied to elements like pi of I. For example, in my notation, if I write pi sigma of I, then that's equal to first apply pi to I and then apply sigma, which is different than writing pi of sigma of I, which if you compared this to the original, you would think, oh, maybe this is equal to that. And if you write right to left, then these things are equal. So we will hardly ever use this notation. So that drawback for us is minimal. But for some people, it's major. And I think, if I recall correctly, I think Dummett and Foote does right to left. And I think Joe Gallian's book works from left to right. I could be, don't quote me on that. But I'm naming probably the 2 most common undergraduate textbooks. If you don't use Cayley graphs, you can get away with writing some groups from right to left and some groups from left to right. For example, in the quaternions, all books are going to write I times j equals k, and they are reading from left to right. But then if you write permutations from right to left, that's okay. But it's just hard to deal with some Cayley graphs being left Cayley graphs and some being right Cayley graphs. So this is a minor trade-off that we will make, but I want to emphasize that pi sigma means, in this lecture series, do pi and then do sigma. And we'll come back to this throughout this lecture. Let's now talk about how to compose permutations, because if we're dealing with groups, we're going to have to multiply or compose elements. And I'll go through this with each of the 3 notations that we've seen. First, let's start with the one-line notation, and I'll do it with an example. And I'm going to use 2 different permutations, pi and sigma, than what I had a few slides ago, because I think these things, this one here illustrates the concept better. As I said earlier, the one-line notation does not make it obvious of how to compose these things, but if we create diagrams from these notations like this, we pull this apart and stick arrows between I and pi of I. So 1 goes to 4 means an arrow from 1 to 4. 2 goes to 3 means an arrow from 2 to 3. 3 goes to 1, arrow from 3 to 1. I think you get the idea. Then doing this permutation, pi followed by this permutation sigma, which is right here, I think you can see what we do. We just concatenate these. We stack them. So 1 goes to 4, which goes to 6. So 1 goes to 6. 2 goes to 3, which goes to 3. 2 goes to 3. 3 goes to 1, which goes to 2. 3 goes to 2. 4 goes to 2, which goes to 1. 4 goes to 1, and so forth. Notice here 5 goes to 6, which goes to 5. So 5 goes to 5. There's a fixed point. Another way to compose permutations is with this permutation diagram notation. So this permutation here in its permutation diagram looks like this. If we first do that one and then we do this one, we get this one here. Let's think about how we did that. So if we start at 1, 1 goes to 4, 4 goes to 6, so 1 goes to 6. That matches what we have up here. Then you can continue with 6, or you can start with 2. 2 goes to 3, 3 is fixed. So remember, this thing here really means that there's a arrow like that. So 2 goes to 3, 3 is fixed, 2 goes to 3. 3 goes to 1, 1 goes to 2, 3 goes to 2, 4 goes to 2, 2 goes to 1, 4 goes to 1, and so forth. 5 goes to 6, 6 goes to 5, 5 is fixed. 6 goes to 5, 5 goes to 4, 6 goes to 4. Now I have the cycle notations down here, but I'll show you how to do it just with that notation on the next slide. So here is that same product of permutations. Let's now do that in slow motion. In the example above, I'm going to focus on the cycle notations. So we start with 1, the smallest digit, and then we read off 1 goes to 4, and then 4 goes to 6. So we write parentheses 1, 6. So 1 goes to 6. Then 6 goes to 5. 5 goes to 4. So we put a 4 after the 6. 6 goes to 4. Next, 4 goes to 2. 2 goes to 1. So we say, hey, look, 4 goes to 1. We've already written a 1. So that means that we end this cycle. And now we're going to start a new cycle. So what do we have left over? We have 2, 3, and 5. So we'll pick the smallest number, 2. 2 goes to 3. 3 is fixed because it doesn't appear here. So 2 goes to 3. We write that. And then we continue with 3. 3 goes to 1. Over here, 1 goes to 2. So 3, well, we've already written 2. So we just end the cycle. 3 goes back to 2. And we start a new cycle because we have leftover numbers. What's left? What about 5? 5 goes to 6. 6 goes to 5. So that means 5 is fixed. Here we don't write. So if you want to write a 1 cycle, 5 goes to itself. But because we typically omit 1 cycles or fixed points, this permutation above is just 1, 6, 4, 2, 3. Moving on, we have seen how to represent groups of symmetries such as V4, Cn, and Dn as matrices. Permuting coordinates of r-dimensional space is also a linear transformation. And indeed, every permutation can be represented by an n by n permutation matrix that we'll call P pi. I'll start with an example of this. We haven't seen this permutation before. I'm doing one of n equals 5 just because I don't want my matrices to get too big. So here it is in one-line notation. Here it is in permutation notation, and here's the cycle notation. The following matrix, P pi, permutes the entries of a column vector. So notice that, well, I'll write down a formula for what I'm doing shortly, but 1 goes to 3, so I make the 1, 3 entry a 1. 2 goes to 1, I make the 2, 1 entry a 1. And 3 goes to 2, I make the 3, 2 entry a 1. And similarly, 4 goes to 5, the 4, 5 entry is a 1, and 5 goes to 4, the 5, 4 entry is a 1. So look what that does to the coordinates. So the 1 subscript gets turned into a 3, the 2 gets turned into a 1, just like up here. And then the 3 subscript gets turned into a 2. And then 4 and 5 subscripts swap places. But now I want to show you something different. If you take the same matrix and you put a row vector here on the left, x1, x2, x3, x4, x5, remember how to do this? It's a little bit weird, but you multiply this vector times the column. So this vector times the first column is just x2. This vector times the second column it picks off x3. This vector times the third column, it picks off x1. And similarly, this times these two columns are x5 and x4. So notice that this permutation is different from this one. Think about how these are different. I claim that they are inverses of each other. I don't have typed up a slide of this, but here's what I want, but I'm going to write it down because I think it's important. So notice that if I want to write down a formula for this pi, and I think you can see how it will generalize, this x3 is x of pi 1. This x1 is x of pi 2. And x2 is x of pi 3, because that's where 3 gets mapped to. So this is x of pi 3, x of pi 4, and x of pi 5. So pi permutes the coordinates like this. So what's going on here? Well, let me write it out and then we'll see why it is. So this, I claim, is x of pi inverse 1, x of pi inverse 2, x of pi inverse 3, x of pi inverse 4, and x of pi inverse 5. Let's think about why that is. So x of pi inverse 1, that's saying, so what is x2? So if I start at 1 and I go backwards, I get x2. If I start at 2 and I go backwards, I get x3. And if I start at 3 and I go backwards, I get x1. So if you think about this, what's going on is if I take this permutation, these actual arrows, and I put it on top of here, like this. And I really say, let's move this x1 into this coordinate. Let's move the thing in the third coordinate to the second coordinate. Let's move the thing in the second coordinate to the first coordinate. That's what we get here. And what ends up here? The thing that ends up here is not pi of, it's not where this gets mapped to. It's what maps to this. That is x of pi inverse of 1, and so forth. So I think this is an important thing to notice, is that if you have a permutation matrix and you multiply a vector on the right, then you are permuting the entries, like, you're sending xi to x pi I. And if you're multiplying by a row vector on the left, you're kind of doing the opposite of that, and that you're sending each I to x pi inverse of I. Let me now formally define a permutation matrix, like what I showed you in the previous slide. Given a permutation pi in Sn, the corresponding permutation matrix is an n by n matrix where the ijth coordinate is 1 if I gets mapped to j and 0 otherwise. So here are several more examples. So 1, 2, 3, 4, I swap columns 1 and 2 and columns 3 and 4, or equivalently rows 1 and 2 and rows 3 and 4. We got to be careful. The row swap and column swaps are not necessarily equivalent, but this permutation has order 2. You see more if you see a 3 cycle, because things are not their own inverses. So if 1 goes to 3, then what that means, using this definition up here, that means that pi of 1 equals 3, so p 1, 3 equals 1, and that's this entry right there. Similarly, pi of 2, well, 2 isn't in here, so 2 is fixed. Pi of 2 is 2, so p2, 2 equals 2. Sorry, not 2, 1. Pi of 3 goes to 4. You can see that right here. So the p 3, 4 entry is 1, and that's this thing right here. So here's another example of a permutation matrix. I'll let you check this yourself. I want to return to the difference of left versus right multiplication and give a little different perspective than what I showed you in the previous slide. So if I have a vector x and I write p pi times p sigma times x, then I'm implicitly multiplying from right to left. I'm first applying sigma, and then I'm applying pi. However, if I want to read from left to right, then I have to put a row vector on the left. So I'll write that as x transpose to emphasize that it's a row vector. So if I first want to apply pi and then sigma, in other words, this product, I have to put x on the left. So start here, then apply pi, then apply sigma. It does not matter whether we use row or column vectors, but we must be careful. Column vectors, like this example, really forces us to multiply right to left, as in function composition. Row vectors, if I use this notation, that naturally corresponds to multiplying left to right, first doing pi, then doing sigma, and that has been our standard. So it's slightly unusual. Usually this is the standard that's used. More books read right to left than left to right when it comes to permutations. I'm going to read left to right, which is going to force me to start with a row vector and then multiply matrices on the right. I want to tie this back to Cayley graphs now, but I also want to just point out that for me anyways, and I think for most people, it's confusing to deal with permutations. And everybody makes mistakes when you're multiplying on the left or multiplying on the right and figuring out how to compose these things. So if you feel like you're making mistakes or you're doing it wrong, that is completely, utterly normal. So what I want to do here is take 1, 2, and 2, 3, multiply these matrices together. So whether you read left to right or right to left, you can't not deny that this product of matrices here is this matrix here, where the 1, 3 entry is 1. So this p 1, 3 equals 1, p 2, 1 equals 1, and p 3, 2 equals 1. And that just means that 1 gets mapped to 3, 3 gets mapped to 2, 2 gets mapped to 1. That's this permutation and cycle notation here. So if I take this matrix and multiply by 1, 2, 3 on the right, I get x3, x1, x2. And let me just remind you that what that is that is x. Do I want to call this pi, or I'm going to call this tau just to be safe, because I don't know if I want to think of this as pi and sigma, or if you want to. So this is x of tau 1, this is x of tau 2, and this is x of tau 3. And again, this here is what I mean by tau. 1 gets mapped to 3, 2 gets mapped to 1, 3 gets mapped to 2. But now let's do this in the other order, or let's multiply a row vector times this same matrix. Again, this row vector times this matrix, which is down here. And now you get a different result. you get x2, x3, x1. And remember from the previous slide that this is x tau inverse of 1, x tau inverse of 2, x tau inverse of 3. So 2 is not what 1 gets mapped to, but it's what gets mapped to 1. So again, if I take this 1, 3, 2, and I do 1 goes to 3, 3 goes to 2, 2 goes to 1, that actually shuffles. Follow these arrows. That's where these things end up. X1 does end up in the third position. X3 ends up in the second position, and so forth. So if I have a Cayley graph, and I'm going to call, this is 1, 2, and this is 1, 3. So my nodes and my colors are matching what I have up here. And right Cayley graph, we read left to right. Then here's how the nodes are labeled. You can check this. And now if I put in these nodes, I put configurations, like what we did in the very first chapter. So let me put the identity state here, x1, x2, x3. And these are our column vectors. So I'm using this convention up here. Well, then, instead of going out over these, I want to compare this to what I have here, where I'm going to put configurations here, but I have row vectors. So here, it's the same thing as, if I take this matrix here and I multiply on the left by x1, x2, x3 are on the right, I'm going to swap the first and the second coordinate. So these three labelings are the same, and also this labeling is the same. The difference is in these two labelings, we get these differences. So this lower left is what I get by first doing the green one and then the blue one. That's what we have right here, 3, 1, 2. But over here, we have 2, 3, 1. Now, I mentioned how these things are, the indices are inverses of each other. But I want to give you another way to think about this. And I claim that in this framework, we are swapping numbers, and in this framework, we are swapping coordinates. And let me show you what I mean by that. So if you start up here, think of these as configurations of x1, x2, and x3. So whenever you follow the green edge over here, I want you to swap x1 and x2 no matter where they are. And when you come over here, you swap x2 and x3 no matter where they are. So here, 1 and 2 get swapped. But now, if we want to swap 2 and 3, and here we're going to swap. So x2 and x3 are in the first and the third positions, respectively, and that gets us down here. Then we swap 1 and 2 no matter where they are. That gets us to 3, x3, x2, x1. Compare that over here. What's happening is we're swapping coordinates. You can see that up here with like this really is being realized by following these arrows with this permutation. So now the green arrow, instead of swapping x1 and x2 no matter where they are, we swap whatever is in coordinate 1 and coordinate 2. And here we swap whatever is in coordinate 2 and coordinate 3, which is different than swapping 2 and 3 no matter where they are. So if we swap the first two coordinates, it's the same as swapping the first two numbers, x1 and x2. We get here, just like we did here. But now, look at 2, 3. So here, if I want to swap things in the second and the third coordinate, we are going to swap x1, x2, and we get, x1, x3, and we get x3, x1s, we get x2, x3, x1. So we're swapping the second and third coordinate, whereas over here, if you look at what we're doing, we are swapping x2 and x3. Those are in the first and the third coordinate, and that's how we get something different. So I recommend pause this, wrap your head around it, but don't think about it too much because it's really easy to go around in circles and confuse it. It's just one of those things where the more you think about it, the more you confuse yourself and convince yourself that the wrong thing is wrong. I think you all know what I mean by that. You've all had that experiences, but really what's happening here is multiplying, using column vectors and multiplying on the right amounts to swapping numbers. And multiplying on the left with row vectors corresponds to swapping coordinates. And not to make things harder, but that's because we are doing things from left to, or we are reading from left to right. If we were to use a left Cayley graph, read from right to left, the numbers and the coordinate things would be swapped. So then the row vectors would be swapping numbers and the column vectors would be swapping coordinates. But that's yet another layer that I really don't want to add. I don't think it's worth wrapping your head. If you try to wrap your head around that one, in addition, you're just going to confuse yourself. Trust me, I've gone around in circles myself many times. The last topic that I want to discuss is a permutation group. And that is exactly what you think it is. It's any set of permutations that forms a group. A fundamental theorem by British mathematician Arthur Cayley says that every finite group can be thought of as a collection of permutations. Formally, it's isomorphic to a set of permutations. I claim that this is clear for groups of symmetries like V4, Cn, and Dn. This is like the symmetries of a rectangle, a pinwheel, and an n-gon. And let me just explain why. It's basically something that we did in the beginning of this lecture. So if you have a rectangle, and I talk about and I label, say 1, 2, 3, 4, I label the corners, then I do a horizontal flip, let's call that H, so flip about this, then that is the permutation that swaps 1 and 2 and 3 and 4. And that's what we were doing. If you have a square and you label 1, 2, 3, 4, and then you rotate, say in that direction, then what this is 1 goes to 4, 4 goes to 3, 3 goes to 2, and 2 goes back to 1. However, for groups like the quaternions, where there's no obvious object that it's permuting, or there's no underlying symmetry, it's not clear why you can think of this as a group of permutations. Again, formally, Cayley's theorem says that every finite group is isomorphic, there's that word again, to a collection of permutations, or in other words, some subgroup of Sn. And I claim that if the group has order n, then you can use that n for the symmetric group Sn. We don't have the mathematical tools to prove this yet, but we'll get a one-line proof when we study group actions in Chapter 5. In this lecture, I just want to give you some intuition as to why this is true and how to think about this, and I think that will pay dividends later on because it'll motivate some of the ideas and the techniques that we will see later. A natural first question that one might ask about this is, okay, suppose this is true. Given a group, how do we associate it with a set of permutations? And that's what I want to show you. Two algorithms that give a strong intuition for why Cayley's theorem is true. And both of these are going to come from Nathan Carter's Visual Group Theory book, although I am using a little different diagrams and groups to illustrate these ideas, but they're basically his algorithms. Here is an algorithm given a Cayley graph with n nodes. First, label the nodes 1 through n. It doesn't matter how. Here's the labeling of the Cayley graph of D3. 1, 2, 3, 4, 5, 6. Next, interpret each arrow type in the Cayley graph as a permutation. So, multiplying by r, you can think of as sending 1 to 2, 2 to 3, 3 to 1, there's that 3 cycle, and 4 to 6, 6 to 5, 5 to 4, there's that 3 cycle. And then the blue arrows, which is multiplying by f, swaps 1 and 4, 2 and 5, and 3 and 6. We see that D3 is isomorphic to the subgroup generated by these permutations in S6. Again, not a proof, but it really seems like this should be the case. Now, I should mention that D3 we actually know is isomorphic to S3. So we can embed this group in a, we don't have to go all the way up to n equals 6 to find a symmetric group that contains this as a subgroup. It's contained as a subgroup in S3 because it's equal to S3. So this is not necessarily going to find the smallest such n, but it will do the trick. And if our group has order n, it will show us how to find a subgroup of Sn consisting of permutations that is isomorphic to our group. Our second algorithm uses the Cayley table. Let's say there are n elements, and we start by replacing the table headings here with the numbers 1 up to n, and then we make appropriate replacements throughout the rest of the table. So we basically just take a table and we replace the group elements, whatever they're called, with the numbers 1 up to n, and then we interpret each row or column as a permutation. So here's an example. Here's D3, and let's do it by rows because it's easier to write horizontally than vertically. So this first row, 1 goes to 1, 2 goes to 2, 3 goes to 3, etc. This is the identity permutation as it should be. This row corresponds to multiplying by r. And if we do on the left, which doesn't match our Cayley graph, but it doesn't matter. So 1 goes to 2, 2 goes to 3, 3 goes to 1. There's 1 to 2 to 3 to 1. And then 4 goes to 5, 5 goes to 6, 6 goes to 4, 4, 5, 6 goes back to 4. Notice that this is actually the, I think this thing was reversed in the previous slide. 4 went to 6, went to 5, and that's because going by row, we're left multiplying. But again, it's not going to matter. And then we do this throughout. So multiplying by f is 1 goes to f, 1 goes to 4, 1 goes to 4, 4 goes to 1. You see that there. 2 goes to 6, 6 goes to 2. You see that right there. 3 goes to 5, 5 goes to 3. You see that right there. So think about, well, first of all, these 6 permutations are a subgroup of S6 isomorphic to D3. And remember that D3 is isomorphic to S3, so this is not the minimal n. But also notice that if we do this by columns, we're going to get something a little bit different. And I'll let you think about whether or not the group is different or whether it's just a permutation of the permutation. So what I mean by that is, let's look at this second row multiplying by r. So 4 went to 5, 5 went to 6, 6 went to 4. So 4, 5, 6 here. If we multiply by r, do the columns, now we're doing right multiplication. And now we get what we got on the previous slide. 4 goes to 6, 6 goes to 5, 5 goes to 4, because right multiplication matches our convention for Cayley graphs. So this is not a proof, but I want you to think about how multiplying by group, if you think about the elements of a group as numbers and you multiply by things with a group operation, you are really just permuting numbers. So when we get to group actions, we are going to formalize this as a group that we say a group acts on itself by multiplication. Going back to that group switchboard analogy, when we press the R button, they all permute themselves like this, this column or this row, and that's gonna prove Cayley's theorem in basically a single line. So we need a lot more structure and theory to get there. So hope you stick around. In the meantime, in the immediate next lecture, we are going to look at 2 special groups of permutations. One of them called the symmetric group, which is the group of all n factorial permutations. And the other one is the alternating group, which is the set of half of those permutations, ones that are so-called even, which means that you can write them as an even number of swapping pairs. And both of these are going to have very, very beautiful Cayley graphs on a number of polytopes and Archimedean solids. So it'll be a lot of pictures. It'll be a lot of fun. Stay with us.